Okay, hi. Today we're gonna talk about the electric field due to a ring of charge. And I'm gonna take this example from Giancoli's book, example 21.9, and I just wanna go over it. The professor went over it in class, and I just wanna go over it in a very detailed way, like he did it, because here in the book they go over it in a way where they expect you to be professional at calculus and know every little thing that they jumped over. So I'm gonna try to go over it in a more detailed way. Therefore, if you're reading it for the first time, or you're new to it, you can ease into it with a little bit more help. So here's a little diagram of our setup, and the problem reads as follows. A ring of charge. A thin ring-shaped object of radius A holds a total charge of plus Q, distributed uniformly around it. Determine the electric field at a point P on its axis, a distance x from the center. Let lambda be the charge per unit length. Alright, let's get to solving it. Okay, here's the diagram. I read it on a separate piece of paper. We have the ring of charge and our point P, which is located an x distance away from the center. So first we're gonna take a tiny length on this ring of charge, and we're gonna call it a differential length, dl. And this differential length also comes with a differential charge on it, since we have charge distributed over it. We're going to take one at the top and one at the bottom, at exactly the opposite ends of each other. And as we can see, the electric field from both of these will come to P, and this is how it goes up and down all the way around. If you would take one here and its opposite, then we would still have a triangle like this set up, just not up and down. It would be more sideways, or depending where we picked it on this side. So we're gonna have, if we're gonna call this and this differential E, which is our electric field corresponding, the tiny electric field corresponding to this tiny length that we picked over here. And this one we can break it up into its components: x direction, y direction. In the y direction, the y from this and the y from this, they're going opposite direction. This one goes up, this one down. Therefore, electric field in the y direction will be 0 due to symmetry. So our total electric field at this point will be our EX. There's nothing else. So total E equals EX. We're gonna start from this formula and gonna start using our electric field formula, which is this one. D equals K dq r square, where K is the same thing as 1 over 4 pi E naught. We're gonna use this one first. We're gonna start substituting in. We're gonna take dE equals, from here we're gonna plug it in, and cosine theta. A little update from geometry or trigonometry: the cosine of this angle we can see is x over h. Solving for x, h times cosine theta. For us, h is our dE. So therefore Ex equals E times cosine theta. Into this one we'll plug in this one. This goes here, and that's why we have this. Now the differential electric field that's due to this differential little charge from that length that we picked is in this formula. We're gonna take a integral of both sides. Here on this side the integral and the derivative will cancel each other, so we will be left with e equals integral of everything that we had, just the same way we write it down. Nothing changes. The book, I want to mention that these problems can be solved also with double or triple integrals, like we learned in Calculus 3. But the book kind of focuses on the ways where we take the several variables and we find relationships between them. We express one of them in a way that contains information from the other ones, and therefore we can use only simple integrals with one integral instead of double or triple. So that's what we're gonna do here. We're gonna look for which of our variables, which are our variables and which are our constants. So here right away we can see that k and our r from our equation, these are constants. This r does not change, it's always the same, and our k is the same, so they're constant. We can get them and move them in front of the integral. Now that we move this in front of the integral, the only thing we have left is dq cosine theta. Now let's work on changing cosine theta into a simpler form. What we can do is again take from trigonometry cosine, and we're gonna use it in our triangle up here. This theta and this theta is the same, and therefore the cosine of this theta will be x over r. We're gonna come back down and substitute into it x over r. Now let's check, is x and r, are they gonna be our variables or are they gonna be our constants? Is x changing? No, it's not. It will be a constant. Is r changing? No. So both of these are constants, and we can again move these out in front of our integral. And after we do so, the only thing is left is dq, our charge. We have the constant, integral, and dq. Now we're gonna start using linear density formula, which is lambda equals q over L, also the charge per unit length. We're gonna take this one and we're gonna turn it into a dq. So from here we're gonna solve for q. Q equals lambda times L. We're gonna take a derivative, and dq equals lambda dl. So we're gonna take this one, plug it into our dq, and our integral will turn into this. Lambda is a constant again, goes in the front, and the only thing we have left in the integral is the length, which is fairly easy to integrate. We do know the length that we are trying to integrate over. What is the circumference of a circle? It is 2 pi r. So we're going to integrate from 0 to 2 pi r. For us, the radius is a. So 0 to 2 pi a. This will be our setup for the integral. E equals all of our constants. The integral going from 0 to 2 pi a. of the length, dl. We solve the integral, simple integral, integral dx is x plus c. Once we solve it, we're gonna have dl turns into L, 2 pi a minus 0, after we plug in the two limits. The only thing left is 2 pi a. Now, this is a lot of things over here. Let's turn it into something prettier. So, if we go back here, we can see that lambda times 2 pi a, which is our length, right? So, lambda times the length is our q. So, we're gonna replace it. And here you go, much simpler way. If we wanna go further and replace the r, the hypotenuse, with more different values, we can continue by using Pythagorean rule, this one, and simply replacing r with x squared plus a squared. From this triangle, we're replacing r with x squared plus a squared under the square root. And there you have it. This will be our final result. This is what the book also works it out to. The next step, what they mention also, is that in case we have an x in the setup, an x that is much larger than this a, then we can consider the a as an insignificant value. Therefore, our formula becomes even simpler down to this. And that would be it. Thank you.